Good afternoon. This is the first video in our series of, I guess we'll call it a gentle introduction to neural networks. All are welcome to watch and comments and any other remarks about these videos are always welcome. I am Bill Sverdlik, speaking to you from Ann Arbor, Michigan. So this is a very large topic. People have been studying neural networks probably since about the 1940s. There were times when there was quite a bit of research being done in it. There were other times where people kind of left them alone. We'll actually talk about when and why that happened. But I think our approach to it is we want to walk before we run, start off with the simple models, and we'll build up to the more complicated ones. So our topic of discussion for today is this thing up here called the perceptron. And the perceptron is probably the simplest neural network it is. It's characterized by just a single processing unit. And we have a picture of a perceptron right here. There are a number of input lines right over here, and there is some processing that goes on in the middle. We'll get into the details of this a little bit later. And then there is a single output line over there. So basically we can think of the output here, at least in this particular model here, the output here is a function of three different inputs. Okay? Now, the idea of a neural network is that we are trying to be predictive. We're trying to decide, we're trying to derive characteristics from data that can let us be predictive about something. So to give you a very simple example, I present an example that's very near and dear to my heart, and that is the idea of just being able to predict whether a student is going to pass a class that they take with me. The idea of this is very compelling, that if I could just look at the student the first day of class, I could make a decision on whether they're going to pass or not, and I wouldn't have to go through the trouble of actually teaching them the material and giving them examinations and grading papers. So I do have some reason to have a neural network that might be able to do something like this. Now, my years of teaching experience have told me that I can be predictive, or I think I can be predictive about a student's success in my class based purely on their height, their weight, and their shoe size. And what I've done over the years is I've actually collected a bunch of data on all of my students, where I've collected their height and weight and their shoe size, and I've also recorded whether they have passed or not. Now, for the sake of brevity, I've only recreated a table with 3 exemplars here. And again, height is measured in centimeters, and we are assuming that weight is measured in kilograms. Shoe size, I'm aiming this video towards Namibians. These shoe sizes wouldn't make any sense here in America, but I think they might make sense in Namibia. I'm not sure. You can certainly let me know. But let's imagine that this is some kind of shoe size. And over here I've indicated whether the student actually passed the class or not. Now, based on these 3 examples here, what I want to do is I want to build a model. I want to create a perceptron so that when some new student comes along, and perhaps the new student weighs 170, they weigh 170, their weight is 70, their shoe size is 34, and I don't know if they're going to pass the class or not. So what I would do is I would put them on this neural network, and the neural network would come back and tell me either yes or no. Now, let's see how this works a little bit, okay? So notice over here I've got 3 input lines, and I've labeled the first input line, which is called I1 here. That's where I'll put the height on. And over here, I2 is the weight. That'll go over here. Over here is the shoe size, I3. And there are some weights that I have associated with each one of these lines. Now, these weights can be any real number. They can be positive, they can be negative, they might even be zero. But what those weights are doing is they're in fact indicating how important I think the particular attribute is in contributing to the whole thing. Now, what happens is these numbers all get fed into the processing unit, if you will, of the perceptron. And we do something here very, very simple. I just multiply the input value times the weight. So over here, I would be putting, if I were to put student 1 onto this neural network, I would have some value for W1. I don't know what it is, but I would multiply it times 190. And then I would take their weight, which is 75, and I would multiply that times some weight W2, and then I would add to that 33, I3, times some weight W3. So I'm going to have these three numbers here that get added up. Now there's one more number that's involved here, and that's what's called a threshold. And again, that is a real number. And the way that this will work over here is that I say it right over here. If I1 times W1 plus I2 times W2 plus I3 times W3, if that's greater than or equal to a threshold, this would output a 1. And if this is not the case, if it's less than the threshold, it outputs a 0. Outputting a 1 indicates that I now have a student that would pass the class. If it outputs a 0, I have a student that wouldn't pass the class. So the big question over here in this model, you can see it right down here, is this problem. We need to figure out W1, W2, W3, and T so that the three examples are predicted correctly. In other words, what I want to do is I'm going to make a guess on W1, W2, W3, and T. I'm going to go ahead and I'm going to put the first example onto the network. If it predicts it correctly, then I don't do anything and I proceed to the second example, okay? If it doesn't predict it correctly, then what I do is I need to somehow adjust W1, W2, W3, and T, okay? And then I would move on to the second example. Now notice I didn't say that my correction is necessarily going to fix the error for number 1, okay? But I will proceed to number 2. And again, I will put these three values on the network and see if my output agrees with what I have over here. Okay? If it does agree, I move on to example 3. If it doesn't agree, I have to somehow adjust W1, W2, W3, and T. And then again, I would move on to the third example. Now the goal of this, and then once I'm done with example 3, I would go back and start all over again with example 1. I keep cycling through these three, and every time I get an error in the output, I keep adjusting the weights in the threshold. My goal is to make it through all three of these and correctly have predicted whether they passed or not. I hope that's clear. Okay, so let's just summarize what we said here, the algorithm, and I was not able to get it all on one screen, but most of it's here. There's only a little bit at the bottom. I'll scroll in a second. So the process that we're talking about here is called supervised learning with feedback. So remember what supervised learning means. It means that we have data that's labeled. And labeled means that there is an attribute that we're trying to be predictive on, and we have examples of them already. Okay? So what we're doing in this situation here is we're observing the behavior of this data. When we put this data on the network, we're observing what the output is, and then we're seeing if it agrees with the output that we have here. If it does agree, we do nothing. If it doesn't agree, we have to change something. So that's just basically articulated right over here. We guess the weights in the threshold. We put an example on the network. Was there a correct prediction? If there wasn't a correct prediction, we need to adjust the weights in the threshold, and we go and we put another example on the network. So we keep doing this. Once we have correct predictions, then the question is are all the examples correct? If the answer is no, then we still have to keep going. Otherwise, we are done, and we would say the network is trained. Now, this drawing here is a little bit misleading for the following reason. Is it possible that you can't train the network? In other words, is it possible that no matter how many times we adjust the weights, and we keep doing this, that we're not going to be able to predict all of the examples correctly? And the answer to that is yes, that is possible. There are several reasons for this. Now, the first reason for it, the most obvious reason, is I was somehow assuming that a student's success in my class is a function of their height, their weight, and their shoe size. Now, I would hope that you would all realize that that's probably a very incorrect assumption, that maybe instead of using these three attributes, what I should have put up here is how many hours a week they study, what classes have they already had, some other things that somehow I don't think that these three attributes right over here are somehow predictive of someone's academic success. So the first problem that you have in which a neural network may not converge to something is the fact that your assumptions may be wrong. In other words, you may be assuming that the output is somehow a function of certain input variables, and in fact, those input variables have nothing to do or very little to do with the output variable. The other question, and this is a much more theoretical question that we're going to return to shortly, is it may be the case that you have to come over here and you have to consider, it says adjust weights and threshold. Well, the question is how do you do that? And there are different ways to do this. These are what are called learning algorithms. There are different learning algorithms out there. And it can be shown that certain learning algorithms just aren't going to converge, and it can be shown that other learning algorithms will converge, but only under certain assumptions. So if those assumptions aren't met, you're in an infinite loop over here. And we are going to return to that question a little later on. I want to talk a little bit more about the kind of data that we can handle in a neural network. And again, you see over here we have a simple perceptron over here. I've got 4 inputs and 1 output. Now, in all of the in the example we've considered so far, the input variables that came over here were real valued. Okay, we had weight and height and shoe size, and what came out of here was a discrete value. It was either a 0 or a 1. So there are a couple of things to be said over here. In the particular model that we just drew, we had input, we had output, and the input over here was real, and the output over here was binary, and it was also discrete. Okay, in other words, in the example we had, the output over here was 0, 1. I'm just going to put over here 0. Actually, I'll draw it this way, that the output was either the set 0 or 1. But it turns out that you can have other combinations of things over here. You can also have binary continuous. I apologize for squeezing it in there. And in that case, the output would be in the range 0 to 1. Okay, and that's kind of an interesting thing to talk about. We could draw a function of what that might look like. In other words, if this is 0 over here and over here is 1, we could have a function that kind of looks like this. Okay, and we can see that all sorts of values between 0 and 1 can be taken on here. So you could think about this. This could correspond either to a probability, or sometimes in fuzzy sets, this could correspond to plausibleness. In other words, if we get a value that is closer to 1, we would go, gee, that's more plausible or believable. If we got a value that was closer to 0, we would say that that's not as plausible, or it may be more unbelievable. Okay, so that would be binary continuous. Okay, there are other things over here. There's also what's called bipolar. And again, that can be discrete. So if it's bipolar discrete, the output would be -1 and 1. And again, you could also have bipolar continuous. I apologize for my really bad handwriting, but I think these are all words that you know. Okay, so if this over here, if this is binary continuous, bipolar continuous, the output function might look something like this. Okay, where we're getting close to 1 over here, and we're getting close to -1 over here. You can have input that's binary. You can have input that's bipolar. Okay, so there are many, many, many different types of inputs and outputs that you can have. When you're dealing with binary discrete or bipolar discrete, sometimes a 1 corresponds to yes or true, and a 0 or a -1 would correspond to no or false. Okay, and the interesting thing about the example that we had, we noticed that there was this threshold. So we had our input 1, W1, plus input 2, W2, plus input 3, W3, and then we said that's greater than or equal to some threshold. Now, think about this number over here and think about what this might look like. Basically, what we're saying here is that if all of these numbers are less than t, the output is 0. So you might come over here and think about it this way. If this value right over here is t, then what we're saying is that we draw a circle right over there, and it's 0 like that. And then if it's t or greater, it looks like that. And of course, this goes out to infinity, and this goes back here to -infinity over there. So this is sometimes referred to as a step function. We came along and then all of a sudden there's a step up here. And we would also note that this also looks very binary to us. It almost looks like a binary discrete function here. Okay. We'll return to this later. And again, we remark that in this particular model, not only do we need to learn the different values of W, but we need to learn the threshold.